Let us take another example. In this case, we have an overhanging beam. It is supported at point A and at point C, and this CD is the overhang. And here you have 6 kilonewton point load. At point B, we have 14 kilonewton point load, and on the portion AC, we have a uniformly distributed load of 3 kilonewton per meter. So the question is, we have to find out the reactions at A, which is RA, and at C, which is RC. So we will go by our whatever we are doing. We will first of all balance the vertical forces, and then we will find out the moment. So let us do it. So RA plus RC is equal to the total load. And what is the total load? The points load, first of all. This is 14 plus 6, and the uniformly distributed load, which is on the part 8 plus 6. So this is 14 multiplied by 3. So this comes out to be 20 plus 42. So this is 62 kilonewton. The next thing is, we will find out the moment about point A. So this is equal to 14 multiplied by 6. This moment is in the clockwise direction. 6 multiplied by 6 plus 4, 10, 10, 18. This is also in clockwise direction. Plus the uniformly distributed load, the total value of the load is 3 multiplied by 14, which is coming out to be this is the total load, and this total load is acting at the center of this AC, which is 14 by 2, and this is being balanced by RC multiplied by the distance 14. Once again, 14 multiplied by 6, then 6 multiplied by 6 plus 4, 10, 18, then uniformly distributed load over the part AC. The total load is 3 multiplied by 14, and where it is acting? At the center of AC. So 14 into 14 by 2. RC is equal to 14 multiplied by 6 plus 18 multiplied by 6 plus 21 multiplied by 14, and this whole divided by 14. So you will get the value of RC. Put the value of RC here. You will get RA 62 minus. So in this way you can find out the reactions. So now we will be discussing the shear force diagram and bending moment diagram. So first of all, we will take up the example of a cantilever beam. So as you are seeing, this is a cantilever beam. One end is fixed and the other end is free, and the span of the beam is L. And a load of W kilonewton is acting at the free end at point B. So we will be finding out its shear force diagram, and we will be drawing its bending moment diagram as well. So first of all, we will take up a section XX, which is, say, at a distance small x from the end B, and we will write down the shear force. We will find out the shear force first of all. Let us say the shear force at the section XX is Fx, and we will be writing down the general equation. So as you know, the the sign convention of the shear force. So at any section, the force on the right going down will be considered as positive. So W will be considered as positive, and it has no relation with the increase or decrease of the distance x. So it is not related to x. So at B, FB is equal to, it is W kilonewton, and you move the section to point A. So at A, this FA is also positive W kilonewton. Next, we will find out the bending moment, and we will write down the general equation of the bending moment. Now, as per the sign convention, you know the force on the right, W, the moment is W into x, and this W into x is going to take the beam in the downward direction. So it is a case of hogging. So minus W into x kilo Newton meter. So at P, x is 0. So MV is equal to 0. At point A, x is equal to L meter. So MA is equal to minus WL kilonewton meter. And the power of x is 1. The power of x is 1. So the variation will be linear. The curve which we will draw, that will be a linear curve. Now we will draw its SFD and shear force diagram and bending moment diagram. So positive W from point B to point A. So this is positive from B to point A. This point is A. This point is B, and this is positive W. So this is SFD, and bending moment diagram at point B, its value is 0. At point A, its value is minus WL. So this is W to L, and the variation is linear, and this is negative. So this is the bending moment diagram of a cantilever beam which is lowered with a point load at the free end. So in this case, a cantilever beam is there, and the loading is uniformly distributed load, W kilonewton per meter. The span of the beam is L. So first of all, we have taken a section XX at a distance of small x from the end B. We will write down the equation, the general equation for the shear force. So Fx is equal to, we are considering the forces on the right of the section. So on the right of the section, the force which we have is W kilonewton per meter, and the length is x. So this is positive Wx kilonewton. Now at point at point B, x, the value of x is 0 because you have put your section at point B. So x becomes 0. So when x becomes 0, FB becomes 0. At point A, the value of x is L meter. So F at A is equal to positive WL kilonewton. As you are seeing, it has a relationship with x, and the power of x is 1, so it is a linear variation. Next, we will find out the bending moment. So the general equation for the bending moment is equal to, the load on the right side is W into x. So, and this is W into x is the total load which is acting on the right side of the section, and this total load is acting at a distance of x by 2 from the section. So we have to multiply this by x by 2, and this force which is acting on the right is taking the beam down. So this is a case of hogging. We will put a minus sign here. So this is W x square by 2 kilo Newton meter. As you are seeing, the power of x is 2, so it will be a parabolic variation. We have to keep this in mind while drawing the bending moment diagram. So at point B, x is equal to 0. So MB is equal to 0. At A, x is equal to L. So M at A is minus W L square by 2 kilo Newton meter. So now we will draw the SFD and BMD. At B it is 0. At A it is W into L, and the variation is linear variation. This point is A. So this is shear force diagram. Just below this we will take up the bending moment diagram, point A and point B. Here it is 0. As you are seeing, at point B bending moment is 0. At point A the bending moment is minus WL square by 2. So this is WL square by 2. I have drawn it in the downward direction. It shows it is negative, and the variation is, it's a parabolic curve. So you have to write it down. The variation is parabolic. The third case is the case of a cantilever beam which is subjected to uniformly varying load. The span of the beam is x. We have taken a section xx, and this is at a distance small x from the end B. So first of all, we will write down the general equation of the shear force, but before that, at this we have, this is W kilonewton. We have to find out the rate of loading. We have to find out the rate of loading at this section. So we will use the this is the rate of loading. This distance is x which we have taken. This distance is L, and this is the rate of loading at this is W. So by similar triangles we have a property W upon L is equal to rate of loading at this section divided by x. So rate of loading at the section is equal to Wx upon L. Now we will write down the shear force equation, the general equation for the shear force. So this is Fx. Now the load on the right of this section is how much? The area of the triangle. What is the area of the triangle? 1 by 2 multiplied by this distance x multiplied by the rate of loading. And what is the rate of loading? Wx by L. So this is Wx upon L. So this total becomes Wx square upon 2L. The power of x is 2. So you have to keep in mind the variation is parabolic. Now at point B, the value of x is 0. So put x 0, Fb is equal to 0. At A, x is equal to L. So F at A is equal to, you put L here, so this will come out to be WL by 2, and this is in kilonewton. So now I am just rubbing this. Now we will find out the equation, this general equation for the bending moment. So mx is equal to, this is the section. On the right side, the force we have calculated. What is the force? Force is Wx square upon 2L. This is the force which is acting on the right of this section. Now, to find out the moment, we have to multiply this by the distance from the point of application of this force. So, where it is applying? This is 1 by 3 of x. From this end, it is 2 by 3. From this end, it is 1 by 3. So, I am just writing down 1 by 3 of x. So, this and this is going down. So, it is a case of hogging. So, I have to put minus sign here. So, this will totally come out to be Wx cube upon 6L kilonewton meter. Now, this you have to take into consideration the power is 3. So, the variation is cubic in nature. You have to draw a cubic curve there to show the variation. Now, at point B, x is equal to 0, so MB is equal to 0. At A, x is equal to L, so MA is equal to, you multiply, you put this x is equal to L in the equation. So minus WL square upon 6 kilonewton meter. Now we will draw the shear force diagram and the bending moment diagram. This point is A, this point is B. At B, shear force is 0, so it is 0 here. At A, it is WL by 2, so and it is positive, and the variation is, power of x is 2, so the variation is parabolic. So we have to write down here, so this is WL by 2 and this is parabolic. Next, we will draw the bending moment diagram. This point is A, this point is B, so this is bending moment diagram. At B, the bending moment is 0, so it is 0. At A, it is minus WL square upon 6. So this is WL square by 6, and the curve is a x to power of x is 3, so it is a cubic curve. So the first thing what we have done is, we have taken a section which is at a distance x, we have calculated the rate of loading at the section by using the properties of similar triangles. When the rate of loading is calculated at the section, we will go for the shear force equation, the general equation for the shear force, 1 by 2 multiplied by the base, which is x, then multiplied by the load, that's this rate of loading. So this will give us the area of the triangle. So this is the area of the triangle, which is the total load which is acting on the right side of this section. At B, x 0, so shear force 0. At A, x is equal to L, so shear force is WL upon 2. The power of x is coming out to be 2, so it's parabolic in nature. Then we have calculated the general equation for the bending moment. So this is the load, Wx square upon 2L, we have calculated there, multiplied by the distance to calculate the moment. So distance is 1 by 3 of x. This total is x, 1 by 3 of x, and it is negative because it is a case of hogging. The power of x is coming out to be 3, so it will be a cubic curve. So at B, x is 0, moment 0. At A, x is equal to L, so moment is equal to minus WL square upon 6. And we have drawn the bending moment and the shear force diagram.